So this constant scalar curvature Kähler metrics business I know nothing about. So that's just because it's a differential geometry conference. Really, I want to talk about stability of algebraic varieties, which is something purely algebro-geometric. But that'd be unfair on differential geometers. So I'm just going to use it as an opportunity. It'd be more like my gauge theory lectures, as to give an introduction to geometric invariant theory, this whole picture of what stability is supposed to have to do with constant scalar curvature Kähler metrics, as mentioned by, for instance, Lou in his talks. So I'll sort of expand on that. And then at the end, I'll describe something about the algebraic geometry. So that'll be a result in pure algebraic geometry, though it does have results in, it does have sort of negative consequences in the study of metrics. So this is all joint work with Julius Ross, who really ought to be giving this talk, but he's busy writing his thesis. So I'll leave that there. Who's here? But yeah, he's sort of too busy writing his thesis, so I'm giving it. Okay, so I want to talk about geometric invariant theory. So this is the algebro-geometric way of taking quotients. So suppose you have a situation where you have a group, a reductive group, acting on a projective algebraic variety. This is a algebraic group. In particular, it would be non-compact. Oh dear. Can I put this in my pocket? Okay. So it'll be non-compact, so the action's not proper. So what happens is you find this is meant to indicate that you can have an orbit tending whose closures, this point is in the closure of both orbits, and this itself might be a smaller dimensional orbit. So you're going to have to throw away some orbits if you're going to form a Hausdorff quotient space. So that's an obvious one to throw away because that's sort of a smaller orbit. But choosing sort of which one of these to throw away is what geometric invariant theory gives you a systematic, clever way of doing. It depends on some parameters, and if you change the parameters, you might throw the other one away. But what you'll end up with is a Hausdorff quotient space. So the proper algebra geometric word is separated. So geometric invariant theory gives you this notion of stable and unstable orbits. You throw away the unstable orbits to get some projective variety. So it's pure algebra. A projective variety is just determined by the functions on it, the sections of this graded ring given by sections of line bundles. So that, in particular, the points of x can be recovered from this by ideals of those functions which vanish on the point. So maximal ideals in here correspond to points in here and so on. So this ring tells you everything. So it's just the functions on the manifold. So similarly, what you do is you want to construct the quotient. You just take the G-invariant polynomials. So if you did have a good quotient, you had x over g. So this is some space here, fibered over g. Then if you pull back functions on g, so sections of some line bundle on g, they sit inside functions. Sorry, not on g, on x mod g. They sit inside functions on x, but they're all constant on the fibers. So you get all the G-invariant functions on x. So this is a good candidate for the functions on the quotient. And it is, in fact, a finitely presented ring by the theorem of, I guess, Hilbert or Mumford. It depends on the case of the group. And the choices which are involved here come from the fact that I picked a lifting. G really acts through the projective linear group up here, but I've picked a lifting to the special linear group, so it actually acts on Cn plus 1, not just projective space. And there's different choices of that. So given a group acting on projective space, there's different choices of its action on Cn plus 1. Because it acts on Cn plus 1, that's nothing other than just the tautological line bundle over Pn minus the zero section. That's just the blow-up of Cn plus 1. So it acts on this line bundle equivariantly, and so it acts on all of its tensor powers. So it acts on this space of sections, so we just take the G-invariant sections. And then, So by just general algebraic machinery, we get a projective scheme as the quotient. And you want to know what that is, which points have we thrown away, which points have we kept, and it comes down to the following. So a point is semi-stable if there are G-invariant functions which don't vanish on it. So that's the first thing you're going to want in order for your quotient to be defined at that point. If you don't have any functions which don't vanish on that point, you won't see it in this ring here. In other words, if you do Kodaira embedding, of course it won't be an embedding, it'll just be a map. I must apologize for MSRI's red pens are awful, and they've gone everywhere and they've smudged everywhere. So what you do is you map your variety using this space of sections here to a projective space. So just do usual Kodaira embedding. This will actually collapse all of the orbits, but it won't even be defined at points such for which all these functions vanish. So you're going to throw away the unstable points, which aren't semi-stable for starters. And then away from the unstable points, this map will be well defined, and will be some kind of quotient, but it will also identify certain orbits. But the stable ones, it'll be a good quotient around the stable, it'll be form a good quotient around the stable points. So the definition of a stable point is where this space of functions actually separates orbits. So not only are the functions which don't vanish on those orbits, but their derivative transverse to the orbits is non-zero. Okay, and depending on your notion of stable, you include this or you don't include this condition here. Okay. So the wonderful theorem tells you what stability, another way of decreeing. This is very algebraic. How do you work out which the stable points are and which the unstable points are? Well, it's sort of purely topological, and it's what you might expect. So there's a wonderful theorem which says that the algebra really sees the topology. There's enough functions, there's enough G-invariant functions to see what you'd expect. So we have this point. Let me see if I've got a diagram on the next page. I'll put the next slide up. So that I can draw the picture. So our group acts on the projective variety, but it also acts on this line bundle over it, because it acts on the whole vector space sat over the projective variety. So the picture is this, that we have orbits. Don't bother with this yet, we'll get to this in a minute. We have orbits here which aren't closed because the group's non-compact, so this orbit might tend to some limit point, so it's not a good closed orbit. But upstairs, it might well be a closed orbit. So upstairs on the line bundle, we may find this orbit shoots off to infinity, and you get a nice closed orbit. If you have a good closed orbit, you stand a good chance of forming a quotient, otherwise you don't. So stable says that this orbit upstairs is closed, and it's of the full dimension. That's this condition here. Whereas semi-stable just says that the origin is not in the closure of the orbit. So if the orbit contains the origin, so under this orbit you can get the closure contains the origin. If you can get closer and closer to the origin, then clearly you're not going to be able to form a nice Hausdorff point in the quotient, because you can get arbitrarily close to the origin and therefore to any point in projective space. So semi-stable says that doesn't happen. Stable says that this orbit's actually closed, and so the functions can distinguish it from all the nearby orbits. And stability is some kind of generic condition. The moment you have one stable point, then actually almost all points are stable. In fact, all points except for some finite union of subvarieties. So there's a risky open subset of points. And then the Hilbert-Mumford criterion further strengthens this and reduces it not to just the group orbit, but in fact one-parameter subgroup orbits. So if and only if the conditions of this theorem hold with G replaced by any one-parameter subgroup, any C star in G, then so if any one-parameter subgroup acting on your point upstairs has a closed orbit, then if that holds for all one-parameter subgroups, then you're actually stable. Okay, so these are the stable one-parameter subgroups, but this has to work for every one-parameter subgroup, remember. Semi-stable ones don't necessarily go off to infinity. They're not closed orbits, but they don't tend to the origin. Then the unstable ones tend to the origin. So is that clear? Is that sort of intuitively obvious? So everything reduces to the action of C star just working out a weight on a line. So you just see where this point goes to. It'll have some limit under this C star action. And what will be happening upstairs is that the line over that limit point is fixed by is acted on by C star. So x tends to some x infinity, some limit point, which is a fixed point of C star. Therefore, the C star is just acting up and down this fiber. In this stable case, it's acting up the fiber. In the semi-stable case, it isn't acting at all. And in the unstable case, it's acting down the fiber. So you just need to compute. You just need to look at the C star action on the fiber over the limit point to determine whether or not the point is stable for this one parameter subgroup. Then you just have to do that for all one parameter subgroups. So this is that statement. C star acts on the fiber, the line over the limit point. If it has negative weight, then it's stable. That means that the C star action is taking you up to infinity. 0 is semi-stable and positive is unstable. From now on, I'm sort of going to blur the distinction between stable and semi-stable because it'll just get too complicated to keep going into all the different distinctions. So all we need to do is just compute this limiting weight for every single one-parameter subgroup of a group. If it's always negative, then you've got a stable point. So that sounds like you're asking for quite a lot, but the generic one-parameter subgroup will be stable, even if your point's unstable. What you want to know is if... Okay. So, the fundamental example, and this will be crucial later on, is just taking n points in CP1. So that's actually a nice algebraic variety at n points. And so it will be the prototype for an algebraic variety later on. In fact, I want to take a length n subscheme. That just means I allow some of the points to be thickened to have a multiplicity, so that it's n total points. That might be less than n geometric points, but this multiplicity adds up to n. So SL2C acts on P1, so it acts on these n points. It actually acts, of course, on the vector space C2, and therefore it acts on its symmetric powers, which are just the degree n polynomials on C2. Okay, so G acts on the space of sections of this ON line bundle over CP1, which is just the degree n polynomials on C2, okay, because it acts on C2. But degree n polynomials on C2 up to scale are precisely the same as n points. Okay, so these n points are just described by a polynomial, and the points are the roots of the polynomial. So the right way to describe n points as a linear space is as the projectivization of the polynomials of degree n. Okay, so SL2C obviously acts on those. And then the stability condition is that less than half the points lie in the same place. Okay, so you're unstable if you have multiplicity n over 2 or more at one point. Okay, so it's some kind of, again, generic condition. Generically, you're stable. You're only unstable if over half your points have coalesced. And that's very easy to prove. So you have a one-parameter subgroup of SL2C. You can diagonalize, so it just looks like this with respect to xy coordinates on CP1. So it just acts like this on x and this on y. And so any polynomial under this action, as lambda tends to 0, well, all the x's get multiplied by lambda to the k, all the y's by lambda to the minus k. So it's clear what happens is the more x's you have, the bigger f... No, that's wrong. Yeah, that's right. The more y's you have, yeah. So the more x's you have, the smaller that part of the polynomial becomes under this rescaling, so that it tends to 0. The more y's you have, so that the smaller I, the bigger this becomes. Okay? So the leading order coefficient, the high... the leading order term with the highest number of y's is the one which dominates as lambda tends to 0. Okay. So what this tends to, up to scale, when I divide out by lambda to the k, or some power of lambda, is it tends to its term with the biggest number of y's, the smallest number of x's. So that's just this, ai x to the I y to the n minus I, where I is the smallest I such that ai is non-zero. Okay, and then the way to, so that's my x infinity, or f infinity, that's the limiting polynomial. And then the line over that polynomial is just represented by that polynomial and all its scalings. And what's the C star action on that polynomial? Well, it's of this weight. So we act lambda to the k acts with weight k times I on here, and n minus I times k on here. So it acts with this weight, sorry, minus n minus I times k on here. So it acts with this weight, and so it's stable if and only if I is less than n over 2, so this weight is negative. So it's stable if and only if f vanishes to order less than n over 2 at x equals 0. Okay, so this polynomial can be written in this form. This is the first coefficient, remember. This is the first monomial in which, with the lowest number of x's, the highest number of y's, which doesn't vanish. It's such that this coefficient doesn't vanish. So in other words, the polynomial can be written as as x to the I times by something. And what we're saying is that I, so the greatest common divisor of f in terms of the x's, is less than n over 2. So in other words, this function vanishes to order less than n over 2 at x. So in other words, the points have less than mass n over 2 at x. Remember, this polynomial represented points via its roots. And what we're saying is we've got less than n over 2 of the points at the origin. Okay, and so that's the origin, of course, wasn't special. It's just to do with the way I diagonalized this. If you did have more than n over 2 points at some other point, do some linear transformation to make it the origin, and then use this C star action to destabilize. Okay, so that you're stable if and only if your polynomial has less than n over 2 zeros at any point, which is the theorem over here. But that relates to something in symplectic geometry. So the general picture is the following. We'll come back to the example in a second. So suppose you also have a metric around, which, sorry, you're on projective space, so use the Fubini-Studi metric. And don't use SLNC, but SUN plus 1. So that preserves the metric as well. So it actually preserves the symplectic structure, the Kähler form. And what that means is the action is Hamiltonian. So given any element of the Lie algebra, so it gives you a direction to move in, a one-parameter subgroup, its infinitesimal action, so the derivative of the action on the manifold, is actually Hamiltonian. So it's given by the derivative, it's given by the symplectic gradient of some Hamiltonian function. Okay, so for every direction in the group or in the Lie algebra, we get this Hamiltonian function. And they glue together to give you something called a moment map. So just think of this as a collection of Hamiltonians, one for each element of a basis of the Lie algebra. So that's the moment map there. That's just this collection of Hamiltonians. If you just pick a basis for the dual Lie algebra or the Lie algebra, this just becomes R Hamiltonians, where R is a dimension of K. But it turns out, a very simple calculation shows you that this Hamiltonian gives you the derivative down. Sorry, there's a constant you've got to fit together. These, at the moment, this isn't necessarily a linear map, so it doesn't necessarily land up in here. There's a constant you have to attach to each Hamiltonian. That if you can do that, a moment map exists. In this case, because everything factors through the action of SUN plus 1 on projective space, you can show there is an explicit choice, and you can normalize the constant so that the following happens. So let me say it again. So we've picked an element of the Lie algebra, so we get a Hamiltonian. We can move down that element of the Lie algebra, gives us a one-parameter subgroup. It gives us a vector field on the manifold, the derivative of the group action. we've lifted all that, of course, to the vector space over this projective manifold. So we can look at how any point moves under this element of the Lie algebra. And what you find is that the derivative of the norm of this point, where you just use the normal norm in Cn, so the normal height up this line fiber here. So the derivative of the norm of the point, the log of it, is given by this Hamiltonian. I should be careful. I've said one little thing wrong. So if I move down, if I move in the Lie algebra of the compact group, the SUN plus 1, then the norm never changes because SUN preserves the metric. I have to multiply it by I and act by that. So in other words, I go down, this is the XV is the vector field given by the compact group action, and I multiply it by J, the complex structure, to give me an action on this vector space. The derivative of the norm, the log of the norm of your point upstairs under that action is given by this Hamiltonian. So in other words, remember the pictures before telling you stable, semi-stable, unstable. Stable is picked out by the fact that this orbit has a minimum, this norm of the log of the norm. So in other words, the minimum of the log of the norm is saying the same that is saying that all of these Hamiltonians vanish at this minimum point. So in the stable case, you get a point where all of these Hamiltonians vanish, i.e. the whole moment map vanishes. So the upshot of that is the following. You might recognize this picture from my gauge theory lectures. I've reflected it to keep you on your toes. So the theorem is that every stable orbit contains a zero of the moment map. There's something you also have to say in the semi-stable case, it's slightly more complicated. So the theorem on the moment map is equivariant under the action of the compact group. It's not the non-compact group. So forming this geometric invariant theory quotient, which means I take the stable points and the semi-stable points, we're not talking about those, and divide by the group, is the same as taking the zeros of the moment map and dividing by the compact group inside it. So here's a stable orbit, a G orbit. If it's stable, it intersects this slice here of the zeros of the moment map in a K orbit, a compact orbit. So this zeros of the moment map, as you see from this picture over here, provides a slice to the imaginary part of the group action. So it takes these minimum norm points, which are perpendicular to this imaginary part of the group action here. So then you just have to divide out by the compact group, and you end up with the quotient. Unstable orbits never reach the zeros of the moment map, so they don't feature in the quotient on either side. Okay, and the example to think of is very simple, although because it's not a projective variety, it doesn't really count. You can't do this via polynomials, but nonetheless. If you take c to the n and try and divide it by the diagonal action of c star, just the scaling action, you need to throw away the origin, that's unstable in some sense, and then you'll get projective space. Alternatively, you can take the zero set of the moment map, that's the sphere of radius a. So the moment map, there's choices in the moment map, but the constant you can choose to be some a squared. So the moment map is norm of the point squared minus a squared. So the zero set of the moment map is those points of norm a, so it's just the sphere. So that's the slice to the imaginary part of the group action, the radial part in C star, the scaling by the real numbers. And then you have to divide by the real part of the group action, which is the compact U1 inside C star. So you divide the sphere by the circle, and you get another description of projective space. So that's the case of one Hamiltonian, and we're just doing some nonlinear version of that with many Hamiltonians. And so in our fundamental example, n points in projective space in CP1, you can find out the moment map. It's very easy to check what the moment map is for the action of SU2 inside SL2C on P1. It's just given by, well, SU2 looks like R3, and the moment map just takes the 2 sphere, which is CP1, and sticks it inside R3 as the unit sphere centered at the origin. So that's not particularly surprising. And what you find is that for endpoints, so the nth symmetric product of P1, these roots of the polynomials, you just get the sum of those moment maps. So endpoints sit inside the 2 sphere, therefore they sit inside R3, and then you just add up those endpoints of R3. So it's the center of mass of the endpoints. Okay, so the moment map from endpoints in P1 is the center of mass of those points inside R3. So the zeros of the moment map are these so-called balanced configurations where the endpoints have center of mass, the origin. And so the theorem, the Kempfer-Ness theorem, says that you're stable, which, remember, we said was that the mass of each point, you had no more than n over 2 points at any fixed place. That Kempfer-Ness theorem says that that's equivalent to there being some transformation of CP1 so that the points become balanced. So that should be sort of obvious. Okay. If you have more than n over 2 points, clearly you're never going to make them balanced. Unless there's one particular semi-stable case where you have n over 2 points at one point and n over 2 points at another point. By SL2C, you can make those antipodal points, and then it is balanced. But the stabilizer of this configuration is bigger, so this is semi-stable, not stable. But anyway. Okay, I hope that's obvious. So that's sort of the standard example of how this theory works. Okay, so we can do this with more general polarized algebraic varieties, not just endpoints. And it turns out to be related to constant scalar curvature. So we have some polarized variety X with a line bundle on it. That Kähler embeds us in some big projective space, a space of sections of the line bundle some high power R, which defines as a point in the Hilbert scheme, so-called Hilbert scheme, parameterizing subschemes of this projective space. So you don't need to know what that is, but it has there is an algebraic variety constructed by Grothendieck which parameterizes subvarieties of this projective space. Okay, so we get a point in that, and that embeds very naturally in the Grassmannian, in a Grassmannian, by just considering all the functions, so sections, all the functions of the sections of the OK line bundle, the degree K line bundle. So, sorry, let me start again. All the degree K polynomials on your big projective space which vanish on X define some subspace of here, of this vector space. So you get a subspace of the degree K polynomials, those which vanish on X. And so that gives you a point of a Grassmannian, and that actually classifies this original embedding. So from your variety, you've managed to get a point in a Grassmannian, which by the Plucker embedding is in some even bigger projective space. And that classifies your variety up to automorphisms of the original projective space, so up to this embedding. I can change this embedding by an automorphism of projective space. So we end up with a point in this high wedge product of some symmetric product. So this is the Plucker embedding. This is the subspace of this space of degree K polynomials, which vanish on X. By wedging a basis of the subspace together, you get a point of this. And then you need to divide by the automorphisms of this projective space to get to go from the Hilbert scheme of subvarieties, which obviously have an embedding, to a Hilbert scheme of actual polarized varieties. And by choosing different line bundles on the Hilbert scheme, you get different notions of stability for this group action. So I'll mention some of those. But just abstractly, you can see this is an algebrogeometric problem. You have a group action acting on an algebraic variety, and you want to know which are the stable points. And the stable points you can parameterize, so you can form moduli of stable varieties. There's lots of technical problems due to boundedness with that Lou mentioned. But I'm not going to discuss those. This red pen is awful. Before we discuss stability, we knew what stability of n points was. It was that you didn't get this more than n over 2 points at any one position. Stability for an algebraic variety is more complicated, so I'll discuss that later. But we can do the symplectic geometry picture more easily. So we have a moment map which is the same as before. It's the center of mass of this variety. So this is like, instead of a finite number of points, we have an infinite number of points. Instead of summing them, we just integrate over them. So it turns out that the moment map, so projective space sits inside the Lie algebra of n plus 1c via a moment map. I beg your pardon, that should say SU. And you take a variety x to its average point in this vector space by integrating. So x is sat inside projective space, restrict the Fabini-Studi metric to it, that gives you a volume form, and integrate this moment map over your variety, and that gives you a point of this one again. Called the center of mass of this variety. And so the zeros of the moment map are balanced varieties, those with center of mass, the origin. And Luo showed that balanced implies Hilbert-Mumford stable. I haven't told you about stability over here yet, but you can see abstractly there is a notion of stability. So you have a group action on an algebraic variety, the Hilbert scheme. And depending on your line bundle, there's different notions of stability. One of them is called Hilbert-Mumford stability. And then there's, oh dear, sorry about this red pen disaster. I thought I'd cleaned it up. So as R goes to infinity, the power of the line bundle I'm embedding by, so that the dimension of the projective space also goes to infinity, then the moment map can actually be expanded out, and its first order term is sort of trivial, and its second order term is the scalar curvature. So I've almost certainly got some references wrong there, so I apologize to anyone. This really isn't my field. And what it turns out is that this balanced condition converges, morally at least, to the scalar curvature being constant. So you restrict the Fabini-Studi metric to your variety. If it's balanced, then this Fabini-Studi metric will have nearly constant scalar curvature. As R goes to infinity, that approximation will get closer and closer. And Donaldson made this more precise. So he could show, sort of in some sense, the easy way that if, of course it's not easy, but that if X does admit constant scalar curvature metrics with the Kähler form in this class, the first Chern class of this line bundle, then they can be moved by an automorphism of the projective space to be balanced. And therefore, by Luo, they're actually Hilbert-Mumford stable. So if you admit a constant scalar curvature metric, you're a stable variety. And Tian announced in his talk last week that Chen and Tian can now show you're actually also K-stable, which is probably the relevant notion for constant scalar curvature metrics. This is probably too strong a notion. That says K-stable. And a partial result in the direction that people really want to go in, which is that if your variety is balanced for all sufficiently large R, so you manage to move all these projective spaces so that you can get a balanced variety, then you can restrict the Fabini-Studi metric to this balanced representative. If that sequence of metrics is convergent, then it converges to something with constant scalar curvature metric, with constant scalar curvature. But no one can prove convergence. I seem to have missed something. Have I missed something? Okay, hopefully it'll come later. Okay, so we have an analog in the endpoint, our baby case. We understood this balance notion. We have the analog of that for varieties. And the infinite limit of that is actually this constant scalar curvature condition. So that's roughly the same as balanced, although that's not proven. What is missing is an algebrogeometric description of stability. So a Hilbert-Mumford criterion. So if you try and take a one-parameter subgroup of this automorphisms of projective space and see what it does to your point of the Hilbert scheme and work out what stability means. So despite the efforts of many, many people like Mumford and Giesecke and Viveg and so on, people have never managed to work out what the Hilbert-Mumford criterion says. So in other words, what's the analog of this condition in the zero-dimensional case? So in order to motivate my discussion of this, I want to discuss the bundle case, which is much better understood and much better known. So we understand what the Hilbert-Mumford criterion says for bundles and what stable bundles are. So let me remind you of that, because I'm going to phrase it in a certain way, which will be analogous to the variety case that will come later. So if I'm taking moduli bundles over a polarized algebraic variety, then this is somehow a more linear problem. It's been worked out. And everything I've said so far has an analog in the bundle case, which is slightly easier, so I'll explain that. So bundles are also classified by a point in a Grassmannian, and also by a map to a Grassmannian. So given a bundle, we can twist it up so it's very positive, so it has lots of sections, so it's generated by its sections. So this is a sequence of vector bundles or sheaves on the manifold. So we take this constant trivial vector bundle, spaces of sections of E twisted up by the line bundle, that should say E tensor L to the R, and this maps to the vector bundle itself. So at each point of the manifold, I get a quotient space of this vector space, so I get a point in the Grassmannian. So I get a map from X to the Grassmannian. And again, the Grassmannian, via the Plucker embedding, sits in a projective space, which sits in a Lie algebra via a moment map. Not very much luck here. And so we have a notion of balanced vector bundles by asking whether this map from X into the projective space is balanced. And Donaldson conjectured yes, I've got two things in the wrong order. I shall come back to that. Donaldson conjectured this should be equivalent to stability. This was proved by Xiaowei Wang. So we can talk, we have this analog of balanced, so a balanced vector bundles. We also find, again, instead of pulling back the Fabini-Studi metric, what we can do is pull back the connection from the universal bundle on the Grassmannian. So on the Grassmannian, we have this universal sequence. So these are the Grassmannian of sections of E to the R. So we have this universal sequence. This is the kernel and this is the quotient bundle. Because this is trivial, there's a canonical connection on this here, given by taking parallel sections here and projecting them down to here and decreeing their parallel. Is that what I want to say? Anyway, or by picking a metric on here, we can get a canonical connection on here. And so when we pull this bundle back, we get our bundle E, obviously, because this was its classifying map. And we can pull back this connection and get a connection on E. So this is the analog of restricting the Fabini-Studi metric to a subvariety. And in the limit, instead of this metric becoming constant scalar curvature, this connection becomes Hermitian-Yang-Mills, at least over a curve. Or in higher dimensions, depends on your line bundle, you can consider Conen-Lung's equation. But this converges to some connection satisfying a nice PDE. And there's also, that's sort of the limit of passing to infinite dimensions. There's also a purely infinite dimensional picture, which I discussed in my gauge theory lectures, where you again have a quotient, but it's an infinite dimensional quotient, which looks very different. So it's the infinite dimensional gauge group acting on the space of connections, and the moment map is this part of the curvature. So zeros of the moment map are Hermitian-Yang-Mills connections. So this finite dimensional picture approximates this infinite dimensional picture. But there's also, so this is all the symplectic geometry. There's also the geometric invariant theory algebrogeometric picture due to Giesecke, Maruyama, and more recently Simpson. And they carry out the Hilbert-Mumford criterion, work out what it means, and find out what stability of a vector bundle means. And it's the following. And I want it. Sorry about this mess. So it's expressible in these terms. So you take the Hilbert polynomial of the vector bundle, dimension of the space of sections of the vector bundle twisted up. And this is given by some polynomial in the twisting. N is the dimension of your base manifold. The first coefficient is given by the rank up to the volume, up to some volume coefficient, which I'm going to ignore. The second coefficient is given by the degree. It's the first Chern class of E evaluated against the Kähler form. And so the monic polynomial, the reduced polynomial, given by dividing by A0, is of this form, where this is the slope. This is degree of the bundle divided by rank of the bundle up to the volume. And then E is stable if and only if for all coherent subsheaves, like all subbundles and also singular ones, we have that the reduced polynomial of F is less than the reduced polynomial of E. This is Giesecke stability. Also, choosing a different line bundle, we have a notion of slope stability, which is what corresponds to Hermitian-Yang-Mills connections that I was talking about before. And that's where this is true in the first order. So instead of comparing these polynomials for large R, we just compare the leading order terms. So this is slope stability, which obviously implies Giesecke stability. So it's that the slope of F should be less than the slope of E. So that turns out to be what the Hilbert-Mumford criterion gives you. It tells you what stability of bundles is. So back to varieties. We have the balance picture. We also have the infinite dimensional picture. So the balance picture converges as you go towards infinite dimensions to the constant scalar curvature picture. You also have the purely infinite dimensional picture, which is like the Atiyah-Bott action of the gauge group on connections. This is due to Donaldson. It's the action of Hamiltonian diffeomorphisms on your manifold. Consider it as a symplectic manifold with the symplectic form given by the first chunk of the line bundle. On the space of compatible complex structures compatible with this Kähler form here on the manifold, you can work out the moment map is indeed the scalar curvature up to a constant, and its zeros are constant scalar curvature metrics. So this suggests that balanced constant scalar curvature and stability should all be sort of equivalent, as they are proved to be in the vector bundle case. And as I say, but we don't even know what stable means for varieties. And what this used to say was that the relationship between stability and constant scalar curvature metrics was suggested by, that's Yau. I hope he never sees what I've done to him. I'm in a lot of trouble if he's watching. In the Kähler-Einstein case, where the polarization you choose, this line bundle is given by the canonical line bundle, so it's C1 of the manifold. And by Tian in general, this was, so he studied this, suggested this correspondence and has studied this in great detail, as you heard in his talk. Please no one tell Yao. Okay, so we want this. That's my survey of constant scalar curvature metrics. Okay, so for the last few minutes, I want to talk about something pure algebraic geometry that's joint work with Julius Ross. So we know that stability of bundles come down to subbundles and subsheaves. So bundles are destabilized by subsheaves. So what about varieties? Well, I mean, for instance, there's one example you could give coming direct from this. You could take the projective bundle of E and ask whether it's destabilized by the projective bundle of a subbundle. You can take the projective bundle of a subsheaf, it's just some blow-up. And you can ask, by analogy, does this destabilize this subvariety? So by analogy with the bundle case, we can ask whether subschemes of a variety destabilize the variety in some sense. We want to see something like this coming from this Hilbert-Mumford criterion. So the Hilbert-Mumford criterion, remember, gives us a C-star action, a one-parameter subgroup action on this Hilbert scheme. So you take a variety, move it in projective space via this one-parameter subgroup. The limit variety will look different. This picture is horribly smudged. So here's your variety xt, that says. You move it by the C-star action, and in the limit, we get something different. But all of these fibers are isomorphic. So what you end up with is a family fibered over C with a C star action, which covers the usual C star action on C, dilating C. Okay? So all these fibers via the C star action are all isomorphic to each other. The central fiber could be different. And what we need to do is calculate the C star weight on this central fiber, but on the line over this central fiber. You have to work out what that line is, and it turns out to be some hideous thing made up of polynomials on X, not surprisingly, and you get some weight, and it depends on two variables, R and K. R was the original embedding in projective space. We had our variety polarized. We took the rth power of the polarizing line bundle, took its space of sections embedded in projective space. Then the way we embedded, that gives a point of the Hilbert scheme. The way we embedded the Hilbert scheme in the Grassmannian was taking degree K polynomials over the projective space and asking which ones vanished on X. And that gives us this K factor. And so we get weights depending on two variables, R and K. And then there's all these notions of stability, and what they amount to is the following. So stable says that this weight is negative for all one-parameter subgroups, so for all these families. For all these families here, this weight should be negative in the stable case. Yep. And in what sense? Well, it depends on which line bundle you choose and what notion of stability you have. So it's in the following sense. You work out that this weight is a polynomial in K of degree K, n plus 1, where the coefficients are themselves a polynomial in R of degree n. And the unstable case is that the weight is positive in the following sense. Hilbert-Mumford stability is that this weight for fixed R is that this weight is positive for K big enough. This is a bit like Giesecke stability. Chow stability for fixed R is that this is true at the leading order term. So that this coefficient here is positive. That obviously implies Hilbert-Mumford stability. So Chow stability is that this leading order coefficient is positive. And that turns out to indeed be the geometric invariant theory, Hilbert-Mumford criterion for a certain line bundle on moduli space. There's asymptotic Chow stability, that this is true for all R bigger, sufficiently large, that this leading order coefficient is positive. And then there's K stability, which says we look at this polynomial in R, and instead of asking that it be positive, we ask that its leading order term be positive. So this is the sort of the weakest notion. This implies the others. Modulation problems. And these correspond to different line bundles on the Hilbert scheme. The sort of standard one that's over there. There's a Chow one. Instead of using the Hilbert scheme, you use something called the Chow embedding, which I haven't got time to tell you about. And then there's a line bundle discovered by Sean, Paul, and Tian, which gives you K stability, as I understand it. There's some problem with ampleness of that line bundle, however. So I'm going to state the results for K stability, because obviously it's simplest. You can do asymptotic Chow, for instance, but the formula becomes much worse. And so we say, I want to understand whether a subscheme can destabilize my polarized manifold. So again, just as in the vector bundle case, we form some Hilbert polynomials. First, we just have the Hilbert polynomial of the variety itself, or its structure sheaf. So again, that's given by the volume to first order, the slope to second order. So this is first Chern class of the manifold times by paired against the Kähler form. And then for Z, we consider the following sort of Hilbert polynomial. So it's take the ideal sheaf of Z, raise it to some power x. So that's just like thickening Z. So this is not functions which vanish to order 1 on Z, but things which vanish to order x on Z. So we're just thickening Z. So Z's as good as any thickening of it. So that's a sensible thing to do by some rational number x. And then we raise everything to the rth power, so things which vanish to order r times x, and we twist by OR. So long as r times x is an integer, this makes sense for large enough r, and you get this similar expansion where the coefficients depend on x, and they turn out to be polynomials in x, so we can actually define this for all real x. When x vanishes, of course, that just means Z has become empty. We ignore Z, and we get back to this position here. So A0 at the origin is just the usual A0, and so on. and then you pick any old c. I don't want to take x too far. I don't want this sheaf to become sort of negative. We want it to remain positive. So we choose c such that this sheaf is still generated by its sections for r sufficiently positive. And then we define the slope to be some kind of, instead of just a1 over a0, it's some kind of integral version of that, some kind of average version of that over x. So it's the integral of a1 over the integral of a0. But there's this strange correction term here that I might say some. I probably won't say anything about. And if you just go back to x itself, if you put z to be the empty set, then you get the slope of the structure sheaf of x. So the ideal, if the z is the empty set, then the ideal sheaf of z is just the structure sheaf of x. And so we get back just a1 over a0 coming from the original Hilbert polynomial. So we have a slope of z and a slope of x. And then the theorem is that if the slope of z is bigger than the slope of x, then z destabilizes x, so x is actually unstable. And by these theorems of Donaldson and Luo and Tian and Chen, that should imply that there is no constant scalar curvature metric whose Kähler form is in this class of this polarization. Okay. So some examples. Well, there's that obvious one that I mentioned before. If you have a subbundle destabilizing a bundle, then you can look at the corresponding projective bundles as a subvariety of this manifold. And then for appropriate polarization, that destabilizes. So the polarization is P of E sits over x. You pull back an ample line bundle for x, and you raise it to a high power, and then you twist by something which is ample along the fibers of the projective bundle. So for m sufficiently large, which means the fibers of this projective bundle sufficiently small, you find this destabilizes. So there's good work in this direction without this sort of formal picture by Ian Morrison from many, many years ago. -1 curves on del Pezzo surfaces often destabilize for appropriate polarizations. This is interesting for two reasons. One is if you use the canonical polarization, the anti-canonical polarization, that's where constant scalar curvature metrics correspond to Kähler-Einstein metrics. Then Tian proved this wonderful theorem that this conjecture of Calabi, that so long as the simplest possible obstruction to the existence of a Kähler-Einstein metric vanished, that was that the automorphism group of x has to be reductive. That comes from all of this stability picture. If you're on a surface and the automorphism group is reductive, then Tian actually showed that there is a Kähler-Einstein metric. In higher dimensions, he showed that's not true. But on the surface, that is true. Well, here this shows that this is not true for other polarizations. So you can produce examples with no automorphisms, and equally all the Fataki invariant obstructions and so on vanish. But it has no constant scalar curvature metric. Some more examples. What you might expect of stability is that it's some generic property. So you can have a family of varieties, most of which are stable, and then some special varieties unstable. So a good example of that is the following. If you take two -1 curves on a del Pezzo surface, let me draw it. So you take a del Pezzo surface with 2 points on it, blow them up. So these are -1 curves. Now move these 2 points together. What the limiting variety looks like is the following. You blow up just 1 point, so the limit of this degeneration here. That gives you a -1 curve. And then you blow up a point on the exceptional divisor instead of disjoint from it. And you get this picture where this becomes now a -2 curve and this is a -1 curve. This -2 curve here, again for appropriate polarizations, can destabilize this manifold. So you can find a situation where you have lots of stable surfaces and the limit surface is unstable. Similarly, P2 blown up in 1 point is the classic example of something which doesn't admit a constant scalar curvature metric because its automorphism group is not reductive. So it can't possibly be stable, but we can also see that from our criterion. The -1 curve actually destabilizes P2 blown up in 1 point. So it's a sensible criterion. It sees it appears to see all known obstructions. So the obvious question is there a converse to this theorem? On some days we think there is, and some days we think there isn't. There's lots of ring theory technicalities to proving the converse. But we're working on it. So the proof of our theorem is to produce a particular degeneration. You need to produce a degeneration, compute its weight, do the Hilbert-Mumford criterion, and try and make it positive to show that something's unstable. The degeneration we take is the obvious one. We have some z in x. We just form the product, x times c, and then you blow up z in the central fiber to get some extra component. Now work out the weight on this. This is called the deformation to the normal cone. Z here can be an arbitrary subscheme. And you get some weight, which depends on r and k. You take some limit. You get some hideous sum that tends to some integral, which gives the criterion that we mentioned. You have to rearrange the sum in lots of subtle, weird ways. But it's all quite well motivated by the vector bundle case. So the obvious questions are, is there a converse to this? Is this the only thing which can destabilize a variety, just as in the vector bundle case? And I guess, since it's a differential geometry conference, you could ask if all of this holds in the non-projective case. So in just the Kähler case, you can do all the bundle stuff, but you can't do the geometric invariant theory because there's no algebraic geometry. But nonetheless, the same stability criterion turns out to be equivalent to the existence of Hermitian-Yang-Mills connections. So you could ask if the same happens here. So if there's no destabilizing subvariety, is there a constant scalar curvature metric? Okay, I'll end there. K-energy notion.
I mean, you need to define the slope, right? No?
I mean, I guess there's a Riemann-Roch formula for it. But I'm not sure what you mean by it. Yeah, okay. Yeah, I don't know enough about K-energy to answer that question.
Another wild question maybe. You just replace, your criterion is for the existence C such that mu C is greater than mu x and it is unstable. So can you reduce that C to some subset of subvarieties, like those C's are invariant under the C star action?
No, because there is no C star action on this variety, right?
Yeah.
I mean, there's only a C star action on the limit variety. But yeah, I mean, we can do things like that, right? I mean, Julius is looking at the moment about unions of subvarieties, intersections of subvarieties. Certainly, if you were to thicken the subvariety, you only make this criterion more stable. So you don't need to consider thickenings, or at least powers of the ideal. You may as well take the smallest version of this subvariety. So yeah, I mean, that's a very good question. You would like to reduce the number of subvarieties you have to check, and so yeah, we're working on that. No, because points in P1 are, that's a different, you've ruined my analogy, Conan. Points in P1 are a hypersurface, right? We're embedding in bigger and bigger projective spaces. So, I mean, that theorem for points in P1 is a theorem about stability of hypersurfaces, which is not what we're using, right? Do you know what I mean, or not? You could embed that hypersurface in higher and higher projective spaces and ask about, instead of it being stable as a hypersurface, just stable as a variety. That would be a completely different question. I don't actually know what the answer to that is. Good question. Hi.
Mark? So K stabilities must correspond to a constant scalar curvature. If you chose one of your other stabilities, are there any like the definition of Yang-Mills that kind of...
Yeah, I mean, I presume there's a PDE. There's a...
Do you know what it is?
Yeah, I mean, you could guess. I'll explain it after. Yeah. Yeah, I mean, just sort of in all these Riemann-Roch formulae, you know how slope usually appears in a Riemann-Roch formula. If you replace all of these representatives, Chern classes and so on, if you replace them by their Chern-Weil representatives, So you get curvatures and their integrals and traces and so on. You can ask that that point-wise, those curvatures, expressions in the curvatures are equal to a constant or something. So Hermitian-Yang-Mills just takes the first term. The appropriate gauge theory equation for Giesecke stability takes the whole lot, right?